Let us now look into a different question. So, if we had lived in a perfect world, we would have peace and harmony everywhere, everybody would be happy, and all graphs would be planar. Unfortunately, we don't live in a perfect world, so there are non-planar graphs, and we have to deal with them as well. And then we have to have a way to measure, I mean, we don't have to, but it would be nice to have a way to measure how far a graph is from being planar. The idea is that if you have a graph where maybe you have just two edges crossing each other, that's different from having a graph where thousands of edges cross each other everywhere. So now we can only tell if the graph is planar or not, but this will help us distinguish between the non-planar graphs. We will look at two ways to measure non-planarity. The first is the crossing number. So the crossing number, kr of g, is defined as the smallest number of crossings we need to draw G in a plane. Pretty self-explanatory name. For example, the crossing number being 0 means that we can draw the graph in the plane with 0 crossings, and that's exactly the statement that the graph is planar. Crossing number 0 means graph is planar. The crossing number of the graph K5, the complete graph on 5 vertices, is 1. So why is it 1? Well, it's not 0, because if it had been 0, it would have been planar, and we know K5 is not planar. But remember what we did when we tried to draw K5 as a plane graph and failed. So we had this cycle, and then we had these two edges going there, these two edges going outside, and the problem was that this missing edge had to cross somewhere. So this shows that I failed drawing K5 as a planar graph, but I succeeded in drawing it with only one forbidden crossing, so I know that the crossing number is 1 because it's not 0. So what is the crossing number of the complete graph, or the complete bipartite graph for that matter? You might want to pause and think, but don't think for longer than 30 seconds. So why didn't you think for longer than 30 seconds? Well, this is actually unknown. It's an open problem. There is no general formula for the crossing number of the of the complete graph or the complete bipartite graph, which is a bit crazy, but that's the case often in graph theory, that as numbers of vertices grow, problems become very complex and difficult. So let's look at another way to measure the non-planarity, and that's the thickness. So the thickness of a graph is the smallest number of planar graphs that you can superpose to form your graph G. So superposing means that you have the same vertices, but you staple the edges on top of each other. This is not just a mathematically interesting gadget, it's actually practically reasonable. If you have seen microchips, there you see that, or not microchips, but circuits, small circuits in computers, you see that you have these, I don't have the terminology for it, but the cables going on top of each other. So you want to make such a circuit as thin as possible, so you don't want to stack so many levels of cords between the different nodes. You want to know the smallest number of layers you need, and that is the thickness. So that's why it's called thickness. And let's look at, for example, K5, since we are at it anyway. So for K5, what you can do is, again, let's draw the same graph. So we did this, and then this, and this. And now this forbidden edge I can't draw here, so I draw a new copy, and I draw the edge here. And now if I put these two pictures on top of each other, I get exactly K5. So for the thickness to be 1, this means that G is planar. I only have to superpose one graph, namely the graph itself, and it's already planar. And since K5 is not planar, it's not going to be 1, but it's 2, as I just showed with my picture. So the thickness of the complete graph on 5 vertices is 2. So this thickness you might want to calculate. And again, as for the crossing number, it's difficult to calculate the thickness exactly, but you can estimate it. Given a graph, if you only know the number of edges and vertices, and you know that the graph is simple, then you can tell that the thickness has to be at least something. So here are two estimates. The first is in terms of the edges divided by 3 and minus 6, and is the number of vertices. And the second is this slightly more complicated number. So what does this notation mean? So the ceiling notation is the smallest integer greater than or equal to a number. So the ceiling of pi is 4, and the ceiling of 3 is 3. So you round up to the nearest integer, and the floor you round down to the nearest integer. So the floor of pi is 3, and the floor of 3 is 3. So let's prove at least this first statement. So a simple plane graph cannot have more than 3 and minus 6 edges. This was the edge estimate we had from before. So if we're stacking a bunch of plane graphs on top of each other, if we stack k such graphs, the total number of edges we get cannot be more than k times 3 and minus 6, because each layer contributes no more than 3 and minus 6. And solving for k, we get that k has to be greater than or equal to m divided by 3 and minus 6. And since k is an integer, you have a whole number of layers, this means that k has to be at least the rounded up integer from this number. So this proves the first estimate, because the thickness is the smallest such k. So if any such k satisfies this, then certainly the smallest such k satisfies this part. Now, I will not go into the detail of the proof of the second inequality, just give you a small hint if you're interested. So you combine this fact with the following equality, that the ceiling of x divided by y, if x and y are positive integers, is the same as the floor of x plus y minus 1 divided by y. I will not prove this fact. You can prove it yourselves if you're interested. But combining this and choosing x equal to m and y equal to 3 and minus 6, you get from the first estimate the second estimate. You have to be careful around when, well, you actually don't need to be careful because we're just assuming that n is greater than or equal to 3. So both these will be positive integers. So this gives an estimate for the thickness. You do not need to memorize this estimate by heart, but it's good to know that using formulas and theorems that we already know, you can give such estimates.